the audience, so feel free to ask him the hard questions. Okay, so our motivation, comes from general statistical learning. So this talk is mainly about machine learning. It's less, but it uses some ideas from this community. So our motivation really came from looking at statistical learning and observing that most of the performance guarantees that we are concerned with in machine learning is kind of this aggregate performance guarantees, average over a population. And really, most of the time, we don't try to say anything about any particular any performance guarantee for a particular instance, let alone what happens in subgroups, okay, or subpopulation. So this is kind of a cartoon that shows how this linear classifier might be giving pretty good classifications on average over a population, but some subpopulations, like this one, you're completely misclassifying half of their the points there. Good. And then this kind of is important in the context of trustworthy AI and machine learning, where a lot of the failures of standard machine learning and AI methods are really highlighted at the individual or subgroup level, and just basically somehow is misaligned with the standard objective that we think about in machine learning. Okay, so this is about this kind of refinement of the standard objectives in machine learning, which really came from a really wonderful paper by Rothblum and Yona from 2021, and it's kind of a like an extension of this, there's a related kind of online variant of this thing from Blum and the course from 2020, and I'll say a little bit more about these two works in a bit, because our work really builds on these two papers. And they're largely motivated by these kind of issues in fairness in machine learning and AI. They are really concerned about not just the classification objectives or loss minimization objectives, but other kinds of objectives they may care about, like calibration. But from us coming from just a standard machine learning background, we're going to just focus on loss minimization, and just to make it even simpler today, we'll look at binary classification. Okay. Actually, our motivation came from this other kind of line of work in machine learning, looking at robustness issues. And another paper that inspired us, this paper on hidden stratification. And they make this observation that when you are using machine learning to train models for prediction and applications, usually the training data, not at all should rarely be thought of as an actual sample from the distribution you care about. It's mainly just a distribution, like a data set of convenience. You just get as much data as you can. Who knows if this is representative of the population you care about? And oftentimes, this data is actually this population from which you got the data is stratified in certain ways. And what matters in the downstream application is really maybe just one stratum from this stratified collection. And so we would like to formalize machine learning objectives or ways of using machine learning, so that even if you don't know what the downstream strata of the population that ultimately matters for the application, very different from the entire population from which you got your data, that somehow you can use machine learning methods that provide some guarantee for the strata that matters. Okay. So kind of at a high level, what we do is we look at this multi-group generalization of standard statistical learning, and there's a lot of things that are very similar to the classical theory for statistical learning, and our main kind of contribution to show how many like the standard sample complexity guarantees in the classical setup really can be ported over to this kind of new multi-group setup. So somehow the statistical aspects are not that different, but there are new kind of algorithmic techniques or principles that we have to develop. And as like an example, in the classical setup, we commonly think that just doing empirical risk minimization over a large population or sample from your population. In multi-group setup, this doesn't even necessarily make sense anymore. You may need predictors that are much more complicated. Okay, so I'm going to try to get through describe to you in what ways the multi-group setup differ from the standard classical statistical learning setup. Okay. So here's our kind of cast of characters for the for this problem. And the first two are kind of standard in the classical setup. So we're going to be thinking of a data being drawn IID from some broad population, we call it P. And just for binary classification problems, we have the feature space and the label space, which would be 0, 1. And we're always going to be thinking about finding classifiers that are good relative to some reference class or like hypothesis or concept class or hypothesis class. We'll call it the reference class H. And we would like to have, find a classifier that does as well as the best classifier from these reference classes. And then the multi-group setup introduces a family of subsets, which we call groups, we call G. These are just, again, you can think of it either subset of X or indicators for these set groups. Eventually, we will require these two sets, H and G, to have finite DC dimension. But for now, don't worry about this. So just kind of as a reminder, so we're all on the same page, the way that the kind of standard statistical learning or agnostic learning goal is phrased is, without any groups involved, is to, if you're given some target excess error epsilon, we would like to take some sample, that maybe grows with how accurate you want things to be, and maybe how complex of a reference class you would like to compete against, get the large sample of data from your population, and then eventually output a classifier that's accurate. And we want error rate not too much larger than the best error rate achievable within this reference class. So this is just the standard statistical learning or agnostic learning setup that we're probably familiar with. And it's well known that it suffices, if you can compute it, to just let F be the empirical risk minimizer within this class H, and that will do this with a very nice sample complexity down. Okay, any questions about this so far? Okay, this should be very familiar. So the multi-group setup in the paper by Guy and Gal, they kind of added this twist where you now think about also not just caring about the error rate with respect to the broad population, but also conditional on the inputs falling within these various groups. So what you like is one classifier F, okay, that's at which high probability, for every group that has sufficient probability mass that your conditional error rate, a rate like this, the error rate of your classifier F given G, which means that X condition on X following G, to be not much larger than the best error rate you can get within this reference class specific to that group G. And not much larger means, plus you're allowed to have excess error at most epsilon. And one basic observation is that it's possible that none of the hypotheses in the reference class can achieve this guarantee, right? Because what might be optimal for one group might completely disagree with what to do for a different group. Okay, so but if you can achieve this guarantee, this multi-group agnostic guarantee, it's kind of a very nice, even for this standard loss minimization setup. It has a lot of nice applications, and one of them is this hidden stratification application that I mentioned before. Like if you have some data set, you collected your training data from a large data, population, but ultimately what matters for your downstream application is a particular subpopulation. If you can ensure that you satisfy this multi-group agnostic learning guarantee, then for every potentially meaningful downstream subgroup or subpopulation or stratum that's kind of well approximated by groups in your family G, we would be able to also say that you satisfy this kind of learning goal with respect to that stratum S. And this requires like some notion of multiplicative approximation of this hidden stratum S with respect to your family of groups G. So this kind of motivates us to develop algorithms that can achieve some kind of multi-group guarantee with respect to very broad families of groups. Okay, so again, this is people have mentioned so far already that this can be easy in some very simple cases. For instance, if all the groups are disjoint, one way to achieve this goal is just to fit a different classifier to every group. I think Adam had written a paper about this at some point. And the challenging case is definitely when these groups overlap, because there might be disagreements about what to do on points that fall into multiple subgroups. Okay. Okay, then maybe for this audience, it's not. I'll just say that, yeah, this kind of makes probably not too hard to imagine that if the group really were disjoint, fitting one classifier to each subgroup would satisfy this guarantee. Surprising. And you get the sample complexity that you would have wanted, and even in the case where you only had to worry about one subgroup. So here, this seems like this is extra factor of gamma here relative to and it's extra plus the BC dimension of the group family G. But this is just saying that because, if you have a small group that only has mass gamma within the broader population, this is just saying that, well, you need to at least just get samples from that population, and then things will be fine. There's this plus DG here. Okay, maybe you wanted this to hold for all of the groups simultaneously or something. Okay, anyway, not so important. Also quite easy is when the groups are not disjoint, but maybe satisfy some structural properties, like they are laminar, they arrange nicely into a hierarchy or something. So the more general case is when these groups can be intersecting in arbitrary ways. And this is where this is a really nice paper by Guy and Gal. They looked at a way of using outcome indistinguishability to provide guarantees in this multi-group agnostic learning setup. And so what they looked at, they developed, kind of a way of using algorithms that guarantee OI to produce a classifier that has this multi-group guarantee, and it has a particular sample complexity that is polynomial in kind of all the right quantities. So it's polynomial 1 by epsilon, 1 by gamma. Gamma is the mass of the smallest group that you're worried about, and then it's only polylogarithmic in the cardinalities of the reference class and the family of groups. So where we wanted to, and what's really nice about this work is that it worked beyond just these kind of loss minimization objectives, and go to objectives like calibration as well. Okay, but one kind of downside is that the way that you have to combine the way you get your final predictors, that is kind of this kind of functional combination of a bunch of reference classifiers and indicators from this family of groups. And we were wondering, one is if there's something that you can do that's much simpler, and two, can you get a sample complexity guarantee that looks much more like what you would have if you had only one group to worry about. So here are our results along these lines. Sorry, question now.
How do you avoid the dependence on how do you avoid the linear dependence on or polynomial dependence on the size of oh, okay, sorry. I think so. Sorry.
There we go. Okay. Okay. So here are our what we were able to come up with. So our first result was a kind of a simpler algorithm that we call PREPEND, and it had like a slightly worse sample complexity in one respect. The dependence on gamma got squared, but then we improved the dependence on epsilon. But it's still not quite optimal. And then maybe the optimal thing that you would hope for is something that we were able to achieve via online learning. And this really, at least when the number of groups is finite and maybe arbitrary, the sample complexity that you would have hoped for had you only worried about like a single group. Complexity just from using empirical risk minimization. Yeah, so the D is the H is the BC dimension of the reference class, DG is the BC dimension of the family of groups.
And you just got the interactions even doesn't matter at all.
That's a good point. Maybe I can say something about that at the end. Yes.
For the online learning method, is it you just basically get randomized one by
the final classifier? Yeah, is some randomized ensemble classifier. Any other questions?
And will you speak to sort of the complexity of learning or the models?
Okay, I'll say something about that in the context of this. I'm not going to really have time to get into the details about the online learning, but it's probably familiar to some people here. Yes.
Is log of G because you're doing online learning and that's why you can't get VC of G?
Yeah, we don't know how to handle infinite learning group. I was hoping maybe get some ideas from Suneika's talk this morning. Okay, let me tell you about the first algorithm. It's really extremely simple. The PREPEND algorithm. So what it's going to output finally is a decision list, kind of a relatively short decision list, where the decision nodes check for membership in various groups from your family of groups G, and the predictors, kind of the prediction nodes, are just the predictions that are obtained by various reference classifiers. So the decision list is just, you know, like a bunch of nested if else then thing. So if you're in group 1, then predict using H1 of X. If you're in group 2, else if you're in group 2, then predict using H2 of X and so on. Okay. So one nice thing about this is you can explain this to anyone. That this is basically all that's happening is that you're ordering the various, you know, maybe some subset of the various groups in your family of groups, and then using a particular classifier specific to that group. Doesn't make sense for like a decision a predicate to appear more than once, like for a particular group. It should only appear at least once. Okay, and then it, you know, it has a particular sample size requirement that we show here. Again, it's, you know, not quite optimal, not quite what we would hope for, but you know, some improvement, at least in terms of epsilon over the prior work. I should say that this algorithm was exactly independently discovered by Ira and Michael Kern and Aaron Roth in a very related context. And I should say that the way that you're actually going to implement this thing, they found a nice reduction to a supervised learning problem, that you can implement this algorithm by using some kind of like supervised learning oracle. So it's efficient in this kind of particular kind of oracle sense. Okay, so here's the whole algorithm. It's literally just this. It looks a lot like the algorithms that we've been seeing for multi-group calibration and so on. So you start with any reference classifier, and then you have a decision list that always uses this classifier. And then what you do is you look at, you try to see if there's, you know, a particular group or a reference classifier such that for that particular group, you know, that group has some reference classifier that has a smaller error, at least based on your training data, smaller conditional error than what you are currently achieving by some noticeable amount. Okay, and if so, then just kind of add a new decision node to the front of this decision list. Okay, prepend this kind of clause to the front of your decision list, and then keep going. So, okay, I already mentioned this. It's kind of basically just determining a particular ordering over some subset of the groups. So it's very easy to understand why, you know, what this predictor is doing, okay, at least relative to the reference predictors. The algorithm, you know, in fact, can kind of loop multiple times, many times. It in fact use the same group in many iterations. So it's not that it always just makes one pass through all the groups. It does something potentially complicated. But the analysis is actually quite straightforward. So, you know, in a particular iteration, we may update the decision list by prepending a new decision node to the front of it, and we get some new decision list. Okay, and we're going to prepend, you know, this new clause to the front. If we do that, that must mean that you know, the error rate of our new decision list. Well, we can first decompose it just using conditional expectations in this particular way. If X does fall into the group GT, they're going to predict using this new reference predictor HT, and that will incur that error rate. And if it doesn't fall into GT, then we predict with the old decision list. And you know, all that happens is that, you know, because we made this update, we're guaranteed that this thing can be upper bounded by the error rate of the old decision list, conditional on this new group that we found. And we know that this means that we made some noticeable progress relative to the old decision list. So this tells us that you cannot, you know, build too long of a decision list. It tells you a bound on how many iterations this algorithm makes. And that's kind of the whole thing. Okay, there's some, there's like an epsilon over 2 because you have to worry about sample averages being close to true averages.
And this is where you're paying for the 1 over epsilon extra factor.
Yeah, there's some extra. You balance something, and something is no longer 1 by epsilon squared. Yeah. Okay, so it would be really nice, I think, this is our first open problem, that it would be really nice to be able to do this with a better sample complexity with something as simple as a decision list. And, we actually kind of tried to do this and we didn't come up with anything. One thing we did observe is that you can't combine just these simple first order statistics in some way to produce a decision list. By first order statistics, I just mean, how large are the groups and what's the best error rate you can achieve using reference predictors within that group. Just looking at these statistics is not enough to tell you, what you should do when in the intersection region between 2 groups. It's just based on these statistics. So somehow you have to at least reason in some way, either implicitly or explicitly, about what happens in the intersection of various groups. So this is our first problem. Can you kind of improve the sample complexity of with something as simple as a decision list? Okay, so since it's so simple, just like make a point that you can actually implement it. This is the same data set from, I think people showed before, from the folks table package that Francis and Morris and others have put together. So very easy to code up. And this is the various ways of dividing up the population to some overlapping groups based on by race, by sex, by age. So they definitely are not disjoint. We compared what happens if we just do a logistic regression using over on the whole population and then apply it to the various subpopulations. We looked at what happens if you just use a specific logistic regression model specific to each group, which is maybe what we want to compare to. And we also compared to just training a single random forest over the entire population, which was supposed to be a pretty good baseline. And in all these cases, the classifier we get using the PREPEND algorithm seems to be pretty competitive. Here's one exception. I think this particular group doesn't have so many data points, so not so much we can do there. What's a little bit disappointing that I didn't show in this slide is that the decision list is extremely simple. It just has actually 2 decision nodes. You should just look at whether in your particular, I think the group is one of the age groups, do something for people with a particular age above some threshold, and then do something else for everyone else.
And the hypothesis class H is logistic regression?
Yeah.
And they all get the same size data set.
Yeah. It's all the same. Everyone's using the same data.
Okay, wait, so just to clarify, so we would expect it to fully beat the other ones if we expanded the hypothesis class, right? Right, so if you run your PREPEND model with a broader hypothesis class that included for example, in that one group where it's not beating group ERM, right?
Well, I guess it is. Okay, I mean, depending on how you want to interpret the error bars, maybe it is beating group ERM, but it's not beating random forest.
Right, but as soon as you expanded your hypothesis class to include random forest, it would just fully beat it, right?
We would hope, at least if you account for the number of data within this group. You would beat it within some error margin. We didn't throw in random forest as one of the reference predictors. Okay, so that was the PREPEND algorithm, which seems like a practical algorithm. So the less practical algorithm is one that's based on online learning, but it does get the right sample complexity, at least if first if you're working with finite number of groups, and if you're willing to just say that this is the best you can do for any finite family of groups. And as you might expect, this is because done by online learning. We're going to simulate an online learning process. This is exactly the setup that Blum and LaCour, Blum and LaCour looked at. And then you do an online to batch conversion at the end. The online to batch is a little bit subtle, but it turns out it's fine as long as we did the Jensen's inequality correctly. But the final predictor is kind of this stochastic ensemble of n base classifiers, where n is the number of training data that you have. So it's not particularly, I don't think it's so practical, and it would be nice to do something better. I guess I wanted to say one thing about how we, why we kind of are thinking about this problem in this particular way. So a lot of, I think the prior work in kind of largely in this space, when you look at just sample complexity as, what sample size do you need to achieve a particular excess error, on all the subgroups, you come up with these kinds of, sample complexity bounds like this. And maybe you see like a 2 or 3, maybe they all kind of seem the same if the epsilon's a constant. But the way we kind of came at this was that we wanted to understand, like, what should you expect had you only had to worry about a particular subgroup? Okay, if you only had to do machine learning for that subgroup. And so when you do that, you would fix the sample size that you have and then ask, how large is the excess error of your classifier for that subgroup? Okay. And so, if you didn't worry about groups, just rewriting what I did on this agnostic learning slide, you would say that, just on the broad population, the excess error you would be able to achieve is like order square root VC dimension of the reference class over n. Turns out this is exactly matching, how you, what kind of how the errors and the uniform convergence bounds for predictors in H. It turns out uniform convergence does hold even for subgroups in roughly the way you would think that, you look at error rates on the subgroups of classifiers from the reference class will be similar to the actual error rates, conditional error rates, and they would deviate by no more than this amount. And this amount is the sum of the 2 VC dimensions divided by the number of samples you see in training examples that you saw in that particular group. Okay. So this is this is just saying something about how well do sample averages converge to the true averages. Doesn't say anything immediately about how well you can do in terms of learning. And this kind of near optimal algorithm based on online learning, okay, at least when this was finite, or sorry, when the number of groups was finite, kind of gets the same thing as uniform convergence in this multi-group learning problem. Okay. And so this is kind of the guarantee that we want. We don't want to think about, how much data do you need for group. We wanted to think about what error rate are we able to achieve for group when, based on a fixed sample size. And this is telling you that, for some group where you don't have so much data, you cannot really expect, the same kind of quality of excess error rates as groups that for which you have much more training data. Okay, so that's all I wanted to say. So I really like this framework, this multi-group agnostic learning setup. It really kind of addresses a lot of these issues, I think, from that have come up in the context of machine learning or trustworthy AI and machine learning. It's also nice because a lot of the same tools that we've been able to use from statistical learning really do come into play here, just that we maybe need to remix some of these algorithmic ideas. And there's some open problems I think that it would be great to work out, to figure out simpler algorithms that are optimal, and also even get fully polynomial time algorithms without this kind of oracle caveat. Okay, thank you very much.
So I'm wondering, so there's like more complicated algorithm, lots of randomization, but it's better rates. Like if we like turn back to decision lists that we learn deterministically, what if you were to can you say anything about this more complicated ensemble? as if it was a decision list with some randomization.
Can you somehow just like represent it as like a decision list?
Yeah.
Not so clear to us how that would work out, but that would be one way to, I guess, simplify things. In some special cases, that like in the case where the groups are hierarchically stratified, you do get something very simple again with the optimal rates.
Great. In the interest of time, let's thank Daniel again and move to the next topic.